Hello friends, let's discuss the next continuous control mode called the integral control and the derivative control mode. Okay, so in the previous lecture what we have done is we had discussed the proportional controller. Okay, proportional control mode. Okay, so what did we do here is we saw that the control output P is equal to Kp into EP with some P naught, and I told you that this P naught is a kind of nominal control output. Okay, nominal control output. What does it mean? So if P naught has some value, let's say for example 50%, it actually means that the controller output will be 50% when the error is 0. At that point in time, the error will be 0. Okay, so the nominal control output is the control output at which the error is equal to 0. Okay. We also saw that this may not be possible always in conditions wherein you have a permanent load change. Okay, permanent load change. So before I get into permanent load change, one important thing which we need to explain here is that how does the proportional controller work without an error? Okay, so it is impossible that proportional controller would work without error EP. Okay, so as you can see, unless there is an error, there will not be any control output for the proportional controller here. Okay. So if you see here, so P is equal to Kp EP plus P naught. Okay. So assume that you had taken this to be some 50% as in the last example. Alright. Now you can only manipulate this Kp into EP term where Kp is a proportional gain. Okay. Now if there is any transient change in the load, okay, the transient change in the load or transient disturbance to the system, then what would happen is it would disturb the system and then that would be reflected in terms of the error EP. Okay, the error EP. And the problem here is that if the disturbance is transient, then the error would be little larger initially, and due to the control action Kp into EP, the error may return to a smaller value. But then we would see that there will always be a term Kp into EP existing. Alright. So therefore, depending on the value of Kp, you will always have some EP value, which is called the offset error. Okay, which is called the offset error. Let me write this properly. This is called the offset error. And therefore, what we did is, especially in the case of a steady state change in the load, or we could call it permanent change in the load, wherein we had to see to it. In the previous example, we took it as P is equal to Kp EP plus some 60. Okay, that means initially it was 50%, and then I had to add another 10%. Okay, that was the example which we took previously. In such a case, what happens is that the zero error condition, right? So this is the new P naught value. Okay, for this error to be 0. Okay, for this error to be 0. The new value of P naught for the error to be 0 is 60%. Okay, as we did in the last example. Okay, so every time what you need to do is whenever there is a permanent load change, you need to adjust this P naught value and bring this error to 0 for nominal value of control output. And therefore, this is called manual reset of P naught value. Okay, manual reset of P naught value. It would be great if we had a kind of setup wherein we can adjust this P naught dynamically, so that every time there is a permanent load change, you would be able to adjust this P naught automatically, and therefore we would call that kind of setup as automatic reset. Okay, we would desire that this P naught should change automatically whenever the load changes permanently or there is a steady state change in load. Alright, so this is the way to understand this one. So we would try to understand what is automatic reset now. Okay, so automatic reset is possible only when the controller output, okay, let me just write it here, if and only if the controller output, okay, increases or decreases when error is not equal to 0. Okay, in the proportional case, even if there should always be a value of error for the control output to be generated. But in integral case, integral controller mode, what is the expectation is that whenever the error is not equal to 0, the control output should change dynamically and then bring the error back to 0. And when the error goes back to 0, the control output should remain at the last value. Okay, we saw this similar phenomena in the floating control mode. Okay, and I told you at that time that if there are several levels of floating control modes at what you call if there are infinite number of levels in floating control mode, then we could approximate it to an integral control mode. Okay, a similar thing would happen here. Okay, now what we do here is, let me write this term, right? So the integral control mode is defined like this. Okay, P is equal to Ki integral 0 to T EP dt. Okay, plus some P of 0. What do you mean by P of 0? This is little different than P0. P0 is a nominal value. An integral controller need not hold it in nominal value, because as long as there is error, it will try to integrate and then make the error 0. Alright, so there will be some initial value of the integral controller. Okay, and that is given as P of 0. Okay, now how does the integral controller calculate the control output? Okay, integral controller does an integration from 0 to T EP into dt. Okay, so it actually calculates the area under the curve multiplied by Ki. Okay, other way of looking at the integral control is to look at the rate of change in control output is equivalent to Ki into EP. Okay, and we will see that this integral controller would be able to reset the P0 value in the proportional control a little later in the lecture series, where we will talk about the P plus I control. Okay, where we have the proportional controller and also the integral controller. Okay, what do you mean by reset? Actually, reset means that for every steady state load change or every permanent load change, you should be able to get back to normal. Get back to normal in the sense that we need to get back to zero error condition. Okay, so that is ensured by the integral controller, since the integral controller will not become zero as long as, if the error is 0 also, the integral controller will hold the last value, and therefore it would ensure that error goes to 0 at any point in time. Okay, so therefore that's the main advantage which we get from the integral control mode. Okay, and the phenomena wherein we did not manually reset the P0 value is called automatic reset in the integral control. Okay, so these are the main points in integral control system. Let's see the plots here. Let's say, for example, you have an error which is constant here, error which is constant here. Let me just write it down properly. Constant error. Okay, so what would happen if you have an integral controller and you have a constant error? What do you expect from the integral control? Okay, so depending on the gain of the integral control, so for example, you're taking two gains, K1 and K2, where K2 is less than K1. You can see from the slope. All right, so the control output would be drastically increase in case the gain is higher compared to the case where gain is lower. Okay, so that means whenever there is an error which is constant, the integral control action would increase constantly with a slope of K1 or K2. Okay, and try to make the error to 0. Okay, this is just a plot wherein it shows that, okay, if the error is constant, how should the integral control increase? It's not completely a feedback loop here. Otherwise, what you would see is, since the integral control action is increasing here, you would expect that the error also should change dynamically here. It is not happening here. Okay, this is just for understanding that how an integral control would take its control action. All right. So this is about the integral control action. You can also see the integral control action in terms of dp by dt. So that's what I told you just before here, that you can write it in terms of dp by dt instead of writing an integration. That means the rate of change of integral error is proportional to the error. Okay, the rate of change of controller output is proportional to the error, and the constant is Ki. Okay, fine. That means larger the deviation in the error, you will find that the rate of change of integral control output would be higher and higher. Okay, fine. That is all about the integral control. But the problem you can see, of course, the proportional controller problems are resolved here by automatic reset. Automatic reset. Because as long as the error exists, the integral controller keeps integrating either upward or downward to make the error 0. So there is no need to adjust this P0 term to a different value every time. Alright, so that's called automatic reset. This would be more clear when we deal with the PI control loop. Fine. Now let's talk about the next control mode, which is called the derivative control mode. Alright, the derivative control mode, wherein the control output is the simple derivative of the error multiplied by a constant kd. So now there is a fundamental problem with the derivative controller, which is the fact that if the error is noisy, if the error is noisy, then the derivative controller, since you have the dE by dt and of course it's multiplied by kd, you would see that the control output would fluctuate very fast. So it is like you take the derivative of the noisy signal, you get a much enhanced version of noise, and that version multiplied by kd will give you the control output. That means this will destabilize the system. So therefore, whenever you use a derivative controller, you never you see to it that the error is not noisy. You take steps such that the measurement signal does not have noise. You keep filters in the feedback loop so that the noise will be filtered out. Whenever you use a derivative controller. That's the main thing. The next problem is if the error is constant. So you can see here, if EP is constant, what do you think will happen? If EP is constant, it's very clear that if EP is constant, derivative controller would not do anything here, right? So it would just give an output of 0. So that means when the error is constant, there is no control action from the integral control. So therefore, in case you use a derivative controller, individually, that is generally not done. You have to use this term called dP by dt plus this P0, wherein P0 is a nominal value. So generally you will not use this derivative control mode individually, but in case you use it, you need to use this P0 value so that you have some nominal value around which you can control the process. But in general, you will not use a derivative control. So whenever you use a combination of controllers, derivative controller will be useful, and only with the fact that you are using a filter in the feedback loop. Otherwise, because of the measurement noise, you would really amplify the control output due to the derivative controller. So this is the most important point which you should remember when we talk about a derivative control. So when the error is 0, or of course the error is 0, its derivative output is 0, that's good. But when the error is constant, the derivative control has no action, and if the error is noisy, that means that noise can come only from the feedback loop, from the measurement. Then also it is not preferred to use derivative controller without using a filter. These are the most important point we should understand in the derivative control. And this important one more point is that the derivative control is also named as rate action or anticipatory control. Anticipatory because you are taking derivative. So this is another name for the derivative control action. Now let's look at the control action of derivative control mode here. You can see how aggressive is the derivative control here. So you have the error plot here, you can very clearly see here, and then you want to calculate the derivative control output. That could be some value of kd. So you see here that depending on the slope of this error curve from point to point, you can see the value. Let's say for example, initially the error value is 0. You are considering the nominal value of control output to be 50%. And depending on the slope, you see the jump in the derivative control. You're just taking the derivative of that slope. Okay, so kd into dep by dt. So that's what is happening here. Okay, so whenever there is this transition taking place, you would see that there is a step change in the derivative output. Okay, so you see there is a decrease in slope here. So from here you have a dip here. Okay, similarly you can see all these plots here. All right. So whenever there is a change in slope from the higher slope to lower slope, okay, then you see a dip in the controller output. Whenever there is a increase in slope, then you would see a rise in the derivative control output. Okay, so this is the way in general a derivative controller works, and as you can see here, it depends all on the slope of the error curve. Okay, the larger the slope, the larger change in the derivative control output, because it is getting multiplied by kd, that means kd into dep by dt. Okay, so this is the operation of a derivative controller with the help of an example which I am trying to put it here. All right, fine. So let's try to do a couple of problems on integral control and derivative controller so that the concepts are clear. All right, so let's try to do a problem on integral controller first. So what is the problem here? So what does it say here? The integral control is used for speed control with a set point of, that means you are having a reference of 12 rpm. That means it's a speed control system with a range of 10 to 15 rpm. Okay, this is the complete range of 10 to 15 rpm. And here the span is 15 minus 10, which is 5 rpm. Okay, the controller output is initially 22%. That means, as I told you, for integral controller you would write it as pi of 0, you could write it as pi of 0 is equal to 22%, right? And you're asking something like that here. So, and also let me just write the ki value here. Ki value is 0.15%, minus 0.15%. Now, what is the question here is, if the speed jumps to 13.5, that means if the actual value is now 13.5 rpm, okay, 13.5 rpm. The initial value, you can assume it as 12 rpm, and the controller was able to control the process, and pi of 0 was 22%. That could be the assumption which can be made. And now, if the speed, the actual value of the speed is jumping to 13.5 rpm, how does the integral control work here? Okay, that's what we need to find out here. Okay, so what does it say here? If the speed jumps to 13.5 rpm, calculate the controller output after 2 seconds for a constant EP. That means it jumps to 13.5 from 12 rpm and remains constant for 2 seconds. Okay, that means that's what we need to check now. So first, let's check the error. Okay, let's check the absolute value of error. So the absolute value of error is the set value minus the actual value 13.5, which is 1.5%, minus 1.5%. All right, this is the absolute value of the error. Okay, let's try to find out the error value in terms of percentage, because control output we need to evaluate in terms of percentage. Okay, so error value in terms of percentage is given by, you write the same thing, 12 minus 13.5, or you can just write minus 1.5 in the numerator, divided by the span. Okay, this you multiply by 100. Okay, so this you are getting it as around minus 30%. This you get it as minus 30%. All right. Now let's try to understand the integral control action, wherein the control output P is Ki integral 0 to T dp dt plus pi of 0. This pi of 0 is given as 22%. Okay, this is the last value at which possibly the error went to 0. Okay, so now we can write this as P is equal to Ki. Ki is 0.15 as you have seen before, 0 to T, and you have this minus 30. What is the value? Minus 30%, right? Minus 30 dt plus 22. Right? So this comes out to be 4.5 into T from 0 to 2 plus 22. Okay. So this comes out to be 9 plus 22. So you get here it as 9 plus 22, which is 31%. Okay. So now the new pi value, new pi of 0 is equal to 31%. Okay. So in case somebody is giving you a new error signal from here, right? So after 2 seconds of the step change in the error, okay, from 0 to minus 1.5%, you see that the integral control action has gone from 22% to 31%. Alright. If somebody is giving you a new change in error, you have to start from the initial value of pi of 0 to be 31%. Alright. So this is the way you need to attempt the problem on integral control action. Okay. So that means you start with some last value of integral control action, and then you add to it the current integrated value. Okay. Now let's try to understand one problem on derivative control. What does it say here? So how would a derivative controller with kd is equal to 4 seconds respond to an error that varies sinusoidally? So it's around EP is equal to 2.2 sine of 0.04t. Okay. So now derivative control action is represented as P is equal to kd dep by dt plus some p naught. Okay. Because I told you that in derivative control action there could be nominal value. Here you don't have any nominal value given, you can take it as 0. You can just take it as 0. Okay, 0%. Okay. Actually you should write it as 0% because the control output is represented in terms of percentage. Okay. Now how do I do this problem? It's quite simple than the problem before. You just have to multiply 4 into dep by dt. So have this sinusoidal signal sine of, sorry, this is becoming cosine of 0. Just cosine, why is this happening here? Okay, so you just write this as cosine of 0.04 into t into the internal thing 0.04. Okay, so what would be the control output? It could be 0.352, is already calculated, into cosine of 0.04. Okay. So this would be the control output if I have an error which is changing as 2.2 sine of 0.04t. Okay. So let's quickly revise what is an integral control and what is a derivative control. Integral control action, the advantage is that as long as the error exists, you keep on integrating, and therefore the control output increases or decreases continuously to make the error 0. Derivative control action, the advantage is that if you need, it could anticipate the changes in error, and since you are having d by dt and multiplied by some gain kd, you can expect that the anticipation, if the anticipation is good, then depending on the slope, you take a control action. Okay, but the problem is that when we have noise, the derivative control action is not preferred unless the noise is filtered in the feedback loop, because in the feedback loop you have the measurement, and therefore you always need to have some filter to filter out the noise. Okay, and therefore derivative control can only be used in situations where the error is not noisy or the measurement signal is not noisy. Alright. So in the next class we will deal with the composite control modes, which are PI and PD control modes, of course the PID control mode, and we will try to do some problems on that. Okay. Thank you.